You learn how to become a competent Python programmer by learning the fundamentals of the language in detail. You'll learn how to navigate complex data structures and accumulate results from them, and you'll learn how to convert data into a format that can be used by other programs. At the end of the specialization, you'll be able to write Python programs of a few hundred lines. You'll be able to use and integrate Python modules into your code. You'll be able to use external tools like APIs by reading their documentation as well. We start from the beginning, and we don't assume any prior knowledge, but we do go deep into the fundamentals of Python to be sure that you understand every aspect of code.
So you want to say something about what's our Runestone interactive environment?
Yeah, so the Runestone Interactive textbook allows you to interleave learning materials with active code assessments that will allow you to actually write code. And we find that writing code is really important because even though you can learn how a concept works in theory, so you might know how some particular feature of Python works, it's really important to actually write code to gain more of a working understanding and to know how to actually apply those concepts in practice. So there's also the Way of the Programmer segments. So most of the course is about how to use Python and learning about Python features. The Way of the Programmer segment is more about how programmers can and should work. Programming is a little bit more of an art than a science. There's lots of correct ways to do things, but there are best practices. So there are things like how to write programs incrementally. In the Way of the Programmer segments, you'll also learn about how to write good automated test cases. So that's going to come in course 4. Until then, we are going to write those test cases for you.
Lauren has created a whole lot of assessments where not only can you run the code in the browser, but it'll tell you whether you got it right or not. And you get that immediate feedback, and you can try it as many times as you want. In fact, we've set up the assessments so that you have to get it right, you get everything right 100% in order to pass the assessment. And the reason for that is we really want you to build mastery so that you don't go on to the later stuff until you've got the early material really solid.
You'll also notice that in all of the projects that you do, you'll find ways of translating the concepts that you learn in the courses and throughout the specialization into your real life. For example, different ways of building programs that might be fun in your job or your school or your work or whatever it is that you do.
So one of the things that I really like as I've watched you all put this together is in Python for Everybody, and you kind of already said this, in Python for Everybody, I really focus on the program. If you get the program, it's like you win, you get the gold star. And we didn't have the time or the luxury to really understand what was going on inside the program. We're just like, we got the program done and we got to move on to the next thing. But with some of the stuff that you have in Runestone, you get to say what's really going on inside of the program and how does this really work. And that's part of the mastery, is so that if you can't, as a programmer, kind of put yourself inside the program and understand how the program is actually functioning, it is difficult to write more sophisticated programs. And so that's where, even though this technically is a beginning course, I think it's really important for people to take more than one beginning course, because you have to go over the same material over and over with, in a sense, deeper understanding each time you go through it.
Yeah, we have this great Code Lens tool I think you're referring to. It lets you visualize what's happening in the execution of the program one line at a time. And you can go forwards and back and see what actually was the value of that variable and when did my list change what its contents were. And so it gives you a way of thinking about it. It's really great for debugging so that you don't have to just do trial and error of let me change something in the code. You can really think through what does a program do.
So another thing that the students always ask me at the end of my course is what next? And I think that it's kind of cool that you've built into this specialization kind of a step into what they're going to do after this. Chris?
Yeah, so one of the things that we've added to this course at the very end is a project course. And that's really to focus people on how to take other APIs that might be out there or packages and use them and do something novel with them outside of just learning. And it gets to this repeated practice comment that you made. And for that, we're actually doing it within the Jupyter environment. So just like you need repeated practice with APIs and with Python fundamentals, there's so many different places that you can write Python code, and Runestone's one of them, and the tools you use in Python for Everyone are one of those. Jupyter is one that's quite common, and we teach that in the data science specialization that students could follow this with. And there's other environments too, and so we're trying to really showcase a diversity of learning environments and production environments for Python.
Programming is not one environment, right? It's not like you have this one thing, you type this stuff in, and that's all the programming. When you're out in the real world, each job often has different kinds of environments.
Yeah, and practice is so important in the context of programming. And I think Lauren has written some great examples of practice problems for you to work on throughout the course as well.
And we have this great practice tool that you'll get to see where it represents to you for review some questions that you've already seen in the past. And it keeps presenting them to you more frequently if you're having trouble, less frequently if you're showing mastery of them. And it's a way to really reinforce what you've got. So look for that practice tool. It also has these fun fireworks that'll show when you've done all of your practice problems for the day.
So as you can tell, we're all really excited to share this material with you, and we hope you have a lot of fun and wish you a lot of luck.
Here at the University of Michigan, our school colors are maize and blue. You might think of them as yellow and blue, but we call it maize and blue. And if I travel anywhere and I have a Michigan logo thing on, someone will come up to me in the airport and say, "Go blue." So on 3, 1, 2, 3. Go blue!
Welcome. If you're returning, we're delighted to have you.
And if you're just joining us for the first time, we're also glad that you're with us. At this point, we're assuming that you're comfortable with functions, with dictionaries, you can extract data from nested data structures, and that you are comfortable with Python's list comprehensions. If you're joining us for the first time, please make sure to look at the video on the Runestone environment, because we'll still be using that for much of what we do here.
I'm Steve Oney.
I'm Paul Resnick. We're both faculty members at the University of Michigan School of Information.
In this course, you'll learn about classes. Classes are nice because they allow you to combine the methods and data that are relevant to some problem into one nice, easy-to-use package. In fact, classes are so nice that some programming languages like Java require you to use classes in order to use the language at all. Python makes classes optional, but as you'll find out in this course, they can make your code much easier to read and write. You'll also learn about class inheritance. Class inheritance allows you to reuse code, which can make your code a lot more concise and easier to read.
You'll also learn about test cases in this course. It's kind of an advanced topic for an intro programming sequence, but we think it's really valuable to get into the habit of writing test cases from the very beginning of your programming career. A test case is a way of specifying what a function or a class should do. If you write some test cases and then you implement your function, if it passes the test cases, you know that the function is implemented correctly. If it doesn't pass, you know you did something wrong with the function.
And you'll also learn how to handle exceptions. So you've probably encountered runtime exceptions before, and whenever you encounter a runtime exception, so when you have a variable that doesn't exist, when you try to divide by 0, whenever something like that happens, then Python just stops running your program and gives you an error message. So we'll learn how to actually handle these kinds of runtime exceptions and give you more control over how Python evaluates your code. In the project for this course, you'll use what you learned and write a game of Wheel of Fortune. And you're going to use classes to represent the human player and the computer player, and you'll use methods to specify how these players can compete against each other.
Dr. Chuck Severance, will make a cameo to show you how classes and inheritance make it easy to implement web programming using the Django framework.
Like previous courses, we'll mostly have screencasts with code examples, but we'll occasionally come on screen in order to introduce words of wisdom or to introduce topics.
I'll offer a few more dad jokes, but not too many this time because this course is mostly Steve.
So let's get started. Bye for now. Welcome back. So in this piece of code, Here we set the instance variable for x for both point 1 and point 2 on lines 8 and 9. Now, even though you can do this in your Python code, this isn't the way that you should set instance variables. So instead, you should set instance variables in what's called a constructor. Now, a constructor is a special method that's meant to initialize Python instances, including instance variables. So the constructor is named what's called underscore underscore init underscore underscore, and it's just a special method with this name underscore underscore init underscore underscore. Now, I'm going to call this, instead of underscore underscore, I'm going to say dunderscore. So that would make this dunderscore init dunderscore. But instead of saying dunderscore init dunderscore, I'm just going to say dunderscore init for now. Okay, so we want to define our constructor, dunderscore init. So the way that we do that is we define this method, and we can say def dunderscore init dunderscore. And init, just like every other method, takes in self as its first argument. And I'm going to pass in two more arguments, x and y. Now, in our constructor, I'm going to say self.x equals x and self.y equals y. Now, if I delete these lines and try to run my code as is, then I'm going to get a runtime error saying that my constructor method takes exactly 3 arguments, but only 1 was given on line 9. And what that's saying is that, okay, so it takes 3 arguments, but self was already provided when we called our constructor. We need to pass in values for x and y as soon as we create instances of point. And so here I'm going to pass in values 5 and 10 for this point, and 1 and 2 for point 2. Now, what happens here is that for point 1, I'm passing 5 in for x and 10 in for y. And for point 2, I'm passing 1 in for x and 2 in for y. And rather than setting the instance variables later on, then what we're doing is we're setting the instance variables in this constructor. So when we say self.x equals x for point 1, that's setting point 1.x to be 5 and point 1.y to be 10. When we do this for point 2, then we're setting point 2.x to be 1 and point 2.y to be 2. So now, if I call getX on point 1, so print point 1.getX, then I should get 5. If I print out point 2.getX, then I should get 1. That's all for now. Until next time. Welcome back. So last time we talked about creating classes. And again, the way that you create a class is you say class, and then the name of the class, which usually starts with the capital letter. So I'll say class point. I'm going to leave open and closing parentheses here. And then you usually declare a constructor method, which is dunderscore init dunderscore. And every method takes in an argument self. And in the case of point, we'll call x and y the arguments of the constructor. And then we set the instance variables inside of the constructor. So I'll say self.x equals x and self.y equals y. In this lecture, I want to give some more detail about what actually happens when we construct an instance of this point class and how Python actually searches for instance variables and methods. So we construct a new point. I'll say point 1 equals point. And then we need to pass in values for x and y. So I'll say that x is equal to 10 and y is equal to 100 for point 1. So let's suppose that we declare two methods, getX which returns self.x, and getY, which returns self.y. When we declare these methods, what Python does is it has some internal representation of the class itself. Now, we've talked about the metaphor of classes as factories, so I'm going to visually represent a class as this factory-like object. So you can imagine these as the smokestacks, and this is the factory. So when we have an init method, we're saying that we have one method inside of the class called _init. And this is a function-like object that lives within the class. So it accepts 3 arguments. It accepts self, and it accepts arguments for x and y. So this method in _init, the constructor, lives inside of the class. And then when we have getX, this method also lives inside of the class. So we have this method inside of the class, getX. In this case, it takes in one argument, which is self. And then we have the method getY. And again, getY lives inside of this class. Now, on line 10, when we create a new instance of point, what this is doing is it's asking the class to create a new instance, and I'm going to represent this instance like so. And every instance has a set of instance variables. And in this case, the instance variables are x, which we set to 10, and y, which we set to 100. Now, I want to go into a little more detail as to how exactly we set these instance variables, x and y, to 10 and 100. In other words, what exactly happens when we say point 10, 100? So I'm going to erase this instance for now. And let's start from scratch. So when Python evaluates the statement point 10, 100, then what it does is it first creates a new kind of blank slate instance. So it creates a new instance of point, and it doesn't have any instance variables at first. The next thing that Python does is it asks, does this point class have a constructor? In other words, this _init method. In the case of point, there is a _init method. So what Python does is it calls that _init method on this empty instance. So what it's going to do is it's going to take this instance and pass it in as the value for self when we call the constructor. And all of this is done before we even have finished evaluating the statement. So we take this instance in, and that's the value of self. And then in this case, we're also passing in 2 additional arguments. We're passing in 10 for x and 100 for y. And when we're passing in values for x and y, these are just function arguments. So in other words, even though x just so happens to be the name of what's going to later on be an instance variable, there's nothing special about this value x. So now we're calling the constructor _init, and we're passing in our new instance, which is blank, and we're passing in again values for x and y. Now on line 3, when we say self.x equals x, then what that does is it sets the instance variable for this instance. So it's setting the instance variable x to whatever this value x that we passed in is. So in this case, we passed in 10 for x, so we're setting the instance variable for this instance, x to 10. Same thing for y. In this case, we're setting y to the value 100 because that was what was passed in. So now we have this instance, and it has 2 instance variables, x and y. That's all for now. Until next time. Welcome back. So suppose that we have some data and we want to use classes to represent that data. So that data might come from a file, it might come from an internet source, or in the case that I'm going to go through right now, it might come from something that we just hard-coded. So in this case, I have a list of city names, populations, and states. So I have city name, Detroit, with population 680,250, and state, Michigan. And I have Ann Arbor, population 117,070, state Michigan, etc. So Pittsburgh, this is the population, state is PA, Mars, small population in Pennsylvania, New York, large population in New York. So let's suppose that I have this data, and let's suppose that I also zipped this data together. So zip is going to take these separate lists and create a list of tuples. So if I print out what's the value of city tuples, I'm going to see that I have a list of tuples where every city name is coupled with its population, which is coupled with the state. So suppose that I want to use classes to represent this data. The first thing that I would ask is, what data do I want to be able to put into every instance? So what should every instance have? So what should instances store? So in this case, let's suppose that I care about all three of these things. So let's suppose that I care about the city name, the population, and the state. So I want every instance to store the city name, population, and state. Then I would ask, what do I want every class to represent? In this case, it's a little bit obvious. Every instance should represent an individual city. And every individual city is going to have a name, population, and state. And I'm going to call my class city. So let's define our city class. I'll do that by saying class, capital C, city. And in the constructor, I'm going to accept a name, population, and state. And I'm going to set instance variables. So self.name equals n, self.population equals p, self.state equals s. And let's suppose that I want to have a str method. So def_str. And I want it to return the city name, state, and then population. So I'll do this dot format self.name, self.state, self.pop. Okay, so now that I have this list of city tuples, and I have a class to represent every individual city, I want to take this list of city tuples and create a list of cities. So let's suppose that I want to have a list of cities. So I'll say cities. I'm going to start it out as an empty list. Then I'm going to loop over every tuple. So I'll say for city tuple in city tuples. For now, I'll just print out what's the value of city tuple. And I can see that I get every tuple on a separate line. If I wanted to, I could set name, population, state equal to city tuple. If I print these out, name, population, and state, then I'll see I have the city name, population, and state in different variables. If I want to create a new city with that name, population, and state, I'll say city equals a new city with name, population, and state. And now city is an instance of the city class. So if I print out what's the value of city, oops, and I also need to spell out population in my str method. Okay, so now I'll see that I am actually calling this _str method on my list of cities. If I wanted to add that city to my list of cities, I could say cities.append city. And by the end of this for loop, cities is going to be a list of city instances. So I can say print cities. And you can see I have a list of city instances. So some shorter ways of doing this. One thing that I could do is I could use list comprehension. So rather than having all of these lines, I could use list comprehension to say that cities equals a new city with name, population, and state for every name, population, and state in city tuples. Now if I do this and I actually print out cities, then I'll see that I get a list of city instances as well. One really short way of doing this is actually, if I do t, I can actually add this star t. What star does is it takes this tuple and expands it into a list of arguments. So this constructs the same thing. I'm going to prefer, however, to instead explicitly get out the name, population, and state. That's all for now. Until next time. Welcome back. So let's suppose that we declare this class to represent a point on an xy plane. So again, our class is called point. We have a constructor that takes an argument for x, for y, and assigns two instance variables, x and y, to whatever is passed into the constructor. Here we also have methods that get the x value and get the y value. And we have an additional method that determines the distance from the origin. So this is, if the point is at x and y, it's going to get this distance from the origin and return it as a float. So let's suppose that we create a point at 7 and 6. If we print out what is the value of this point, so I say print p, then Python gives us back just information saying that this is a point object. It has no information about where the point actually is. So for example, if I had a second point at 8 and 9 and printed out p2, I have no way of telling that p and p2 are different points. So classes can have an optional method called _str. So def _str _. And just like every other method, it accepts self as the first argument. And what this _str method does is it tells Python how to represent that object when you actually print it out. So if I specify that str should print out just point by returning the string point, now when I print out both of my point instances, you can see that I get point. If I instead print out point 1, 2, 3, then I'm going to print out point 1, 2, 3. So whatever gets returned by this _str method is what gets printed out when we convert this point object to a string in order to print it. So for points, we might want to have something like point and then maybe the x and y position. So what I might say is point at x and y by saying point.format and self.x, self.y. Now, when I print out point p, then I'm going to get point at 7 and 6, because here 7 gets substituted for self.x, 6 gets substituted for self.y, and self.x goes into the first slot, self.y goes into the second slot. And so now I can tell both of these points apart, and when I print out the instance, then I actually get something useful for point. So when you create a class, you often want to set the _str method in order to get more readable and understandable things to print out when you actually print out any particular instance. That's all for now. Until next time. Welcome back. So suppose we have our point class from before, and we have a constructor, _init_, and _str_ to represent how we represent any instance as a string. Now suppose that we have 2 points as well, point 1 at -5 and 10, and point 2 at 15 and 20. So suppose that we wanted the ability to be able to add points together. So for example, if we take point 1 plus point 2, then we might get something like 0.12. And we might want to add points together by adding their x-coordinates. So -5 plus 15 would give us 10. And then adding our y-coordinates. So 10 plus 20 would give us 30. So our new point, P12, would be at 10 and 30. So if we write in our code, just to say print out the value of P1 plus P2, then we're going to get an error saying that we can't add points. In other words, when we tell Python that we want to add these 2-point instances, then Python doesn't know how to actually take these instances and produce something that represents their values added together. But we can override a method called _add_ that will tell Python how to actually add 2 points together. So if we say def _add_, so add is going to take in self, but it's also going to take in what we're expecting to add to self. So I'll call this other point. So for example, when we print out the value of P1 plus P2, then P1 gets passed in for self, and P2 gets passed in for other point. Now, if we want to take the x-coordinates and add them together, and then take the y-coordinates and add them together, and return a new point, then what we can say is we want to return a new point whose x is equal to self.x plus other point.x, and whose y is equal to self.y plus other point.y. And now as soon as we define this add method, then when we print out the value of point 1 plus point 2, then we're going to see that we get a new point at 10 and 30. Again, this is just 15 plus -5 gives us 10, and 10 plus 20 gives us 30. Beyond add, there are several other methods that we could override. So for example, there's subtraction. So for example, if we wanted to be able to print out the value of P1 minus P2, then we could define this subtraction method. And suppose that we wanted this to be defined as self.x minus other point.x and self.y minus other point.y. Then now we have the ability to quote-unquote subtract 2 points together. There are many other methods that we can override, but they follow the same pattern as add, sub, and they all start and end with underscores. That's all for now. Until next time. Welcome back. So you've already learned that functions and methods can return any kind of value as their return value, but one thing that's worth noting is that they can specifically return other instances. So let's suppose that we have this point class, and this point class has a constructor, and the constructor sets 2 instance variables for x and y, and we have methods getX to return the x instance variable, getY to return the y instance variable, and then distance from origin to return how far x and y are from the origin. Now, suppose that we wanted to define a new method here. Suppose that we wanted the ability to accept 2 points and return a new point that was halfway between the two. So, for example, here I have point P and I have point Q. And let's say that we wanted a function that would return a new point that was halfway between point P and point Q. And let's call that function halfway, and let's make it a method on every point. So for example, if I say P.halfway when called with Q, then this should return a new point that is halfway between P P and Q. So if I call this midway, so I'll say mid equals P dot halfway Q, then I want this to return a new point. In this case, the x should be halfway between 3 and 5, so the x should be 4, and the y should be halfway between 4 and 12, so the y should be 8. So let's define that method. So I'm going to say def halfway, like every method except self, and then I have a target, and we want to return a new point that's halfway between self and target. So I'll say the x, so the mid x is equal to the average between self.x and target.x. So self.x plus target.x divided by 2. Mid y equals self.y plus target.y divided by 2. And I can return a new point, return a point whose x is mx and whose y is my. And now if I print out what the value of mid is and run my code, then I'll see that I get x equals 4, which is halfway between 3 and 5. And I'll see that y is 8, which is halfway between 4 and 12. And again, note that mid is a new instance of my point class, so I can do things like print out mid.getX, and I can print out mid.getY, and I'll get 4 and 8 respectively for those values. That's all for now. Until next time. Welcome back. So we've already seen that every instance of a class can have its own instance variables. So for example here, we have a point class, and inside of the constructor _init, we can see that every point instance has instance variables for x and y to represent the position of that particular point. Now, for example, here when we create a new instance of point with x equal 2, y equal 3, then suppose that our point class is represented with this notation again. So this represents our point class. And P1 is an instance of the point class that has instance variable x set to 2 and instance variable y set to 3. Now, we also have another instance of our point class, so that's P2, and P2 has x set to 3 and y set to 12. Right, so we have P1 and we have P2. So one thing that I want to note is that instances have their own variables, but classes can have their own class variables. They work just like instance variables, except that they belong to the class itself. So for example, here, the point class has its own class variable called printed rep. So I'm going to write that inside of the class point, so I'll say printed rep. Is set to a star. Now, the point class also has these methods, which are also a form of class variables. So we have _init, and its value is some function. And we have this graph method, whose value is a different function. Now, whenever Python searches for anything of the form instance name dot instance var, so for example, if we're doing p1.graph or p2.graph, or even something like print p1.printed rep or print p1.x, then the search order that the Python evaluator goes in is it first searches inside of the instance. So in this case, if we're searching for p1.x, then it searches inside of p1 and it finds x there and it evaluates that to be 2. If it doesn't find an instance variable with the name x, or in this case, let's go with the example of p1.printed_rep. So if we're searching for p1.printed_rep, Python first searches inside of the instance p1. It doesn't find it there, so then it searches inside of the point class, and that's where it finds it. When we say p2.graph, Python first searches inside of p2. It doesn't find it there, and so it searches inside of the point class where it finds it. If we had something like print p1.z, then Python would first search inside of p1. It wouldn't find z there. It wouldn't find z there. It would then search inside of the point class. It wouldn't find z there either, and so it would give us a runtime error. Now, the way that we define this point class, if I erase these annotations, the way that we define the point class is that we have this graph method, and what graph does is it kind of forms a text graph, or a textual representation of a graph that contains this point. So if I erase my annotations and I run my code, so here I create 2 instances of point, one at 2.3, one at 3.12, and I call p1.graph, and what that does is it creates a little textual representation where here you can see kind of an x-axis, here you can see kind of a y-axis, and I can see that my point p1 is at 2, so 2 and 3, and I can see that my point p2 is at 3 and 12. Inside of this representation of graph, I refer to self.printed_rep. So you'll note that here, printed_rep, again, is a class variable that's set to a star. If I change printed_rep to be, let's say, a lowercase x, then you'll see that printed_rep changes for both p1 and p2 when we actually call the graph method on both of them. So that's an example of how classes can contain variables. So again, we have instance variables that belong to every particular instance, and we have class variables which belong to a class. Here, technically, there are 3 class variables. There's printed_rep, _init, and graph that all belong to the point class. That's all for now. Until next time. Welcome back. Before you write any code for classes, there are a few questions that you should ask yourself. First is, what kind of data do you actually want to represent with your class? Is it a list of songs? Is it a list of students, a list of cars, etc.? And then once you know that, then you should ask yourself, what does one particular instance represent of this class? So if it's a list of songs, one particular instance might represent a song. One particular instance of a list of students might represent one particular student. Then from there, you should ask yourself, what are the instance variables? What's unique to every instance that I might have? So if it's a list of students, it might be something like a name, a student ID. If it's a list of songs, it might be the artist, the track name, the length, etc. And then after you know that, you should also ask, what methods might you actually want? So if every instance is a particular song, then you might have a method, for example, to ping an external API to get the lyrics for that song. If it's a student, you might want to have a method to, for example, send a message to that student. It depends, again, on what your instances represent. Then finally, you should ask yourself, what does a printed representation of an instance look like? So if I print out a particular song, then I might want to print out the track name, and then the album name, and maybe the length. And you should have answers to all of these questions before you start writing code for classes. Now, it's important to note that designing class is really more of an art than a science, and it's very common to also refactor or rewrite classes in instance variables and methods, even for experts. But all of this comes more with practice. That's all for now. Until next time. Welcome back. So I'm going to start by defining a class to represent a person. So I'm going to say class person, and let's say that every person has a name and a year that they were born. So I'm going to create a constructor, def_init, that accepts a name and a year born, and assigns instance variables for name and year born. Self.name equals name, self.year born equals year born. Now, let's suppose that I also want to have a method getAge. So getAge that takes this year born, and let's suppose that we have a current year. So I'll define current year to be 2019. So getAge is going to subtract current year. So I'll say return current year minus self.year born. And let's suppose that we also want to override the _str method. So I'll say def_str to print out self.name. So I'll use the .format method and .format self.name and self.getAge. Okay. So now we have a class to represent a person, and every person has a name and a year that they were born. So if I create something like Alice equals a new person named Alice Smith, and I print out the value of Alice, I also have to pass in a year born, so I'll just say 1990. Whoops. I need one more closing parentheses here. Okay. So now I can see that Alice Smith is the name and 29 is the age, given that the year born is 1990. Of course, we're just going to ignore things like exact birthdays for this purpose. Now, suppose that I wanted to define a new class to represent a student, and what I want a student class to have is everything that a person has plus one more thing. So I want students to have this notion of knowledge. So what I'm going to do is I'm going to start by just copying and pasting my person class. So I can do this, and then let's suppose that I want to have another instance variable named knowledge, which I'll start out as 0. So I'll say self.knowledge equals 0. And I want this to be student instead of person. And let's suppose that I want to have this other method on student named study. So def study. And whenever a student studies, then their knowledge should go up. So I'll say self.knowledge plus equals 1. Okay. So now, if I define Alice to be a student instead of just a person, by saying Alice equals a new student, then you can see that I still get Alice Smith, age 29. If I print out Alice.knowledge, then I should get 0. If I tell Alice to study and then print out Alice's knowledge level, then I'm going to get 1. Now, this is a fine way of defining both a person class and a student class, but there's a much easier and more concise way of actually doing this using something called inheritance. The idea of inheritance is that you can define classes that inherit from other classes. So in other words, they take all of the instance variables, all of the methods that that other class has, and then they can add more instance variables and more methods. So in this case, every student is a person. It's not true that necessarily every person is a student, but every student is a person. So what I'm going to do is I'm going to say that this student class should inherit from person. So a student should have everything a person has plus more. Now, the way that I say I want student to inherit from person is by putting parentheses after the class declaration here and putting the class that I want to inherit from inside of those parentheses. So I'll say that every student is a person. So now that I do this, I can get rid of some of the repetitive parts of the student class. So here, for example, getAge is a little bit repetitive. I don't need getAge in both student and person because getAge is already inside of person. So I'm going to remove getAge from the student class. I'm going to do the same for the _str method. And I'm going to do one more thing as well. So this setting self.name and self.yearborn is a little bit repetitive with the person class setting self.name and self.yearborn. So in the constructor for the student, I'm going to say that I want to call the constructor this method of person. And the way that I'll do that is I'll say person dot _ init _ and I'm going to pass in self, name, and year born. Now, when I do this, I'm going to call this init method, or the person constructor, on this new student. So this is going to call this method, and then this method is going to set instance variables for name and for year born automatically. So let's test this out with Alice and be sure that our code still works. So you can see again, we have our student, Alice Smith, born in 1990. And if I still run this code, you can see that after Alice studies, then Alice's knowledge is 1. But now if I print out alice.getAge, you'll see that Alice is 29. If I print out Alice, then you'll see that we get Alice Smith, age 29. And the important part here is that even though Alice is a student, and even though the student class didn't directly define _str or getAge, I'm able to call both of these methods on Alice because Alice is a student and student inherits from person, and the person class has these methods getAge and _str. That's all for now. Until next time. Welcome back. So we've already covered inheritance, but it's worth talking about when we actually want to inherit and how we want to inherit at times. So in general, the way that Python uses inheritance is that let's suppose that we have a superclass. So I'm going to represent classes by this factory. I think a factory is a good metaphor for classes, a factory for constructing instances. So let's say that this red factory represents a superclass. And a superclass is the class that we're inheriting from. Let's suppose that this blue factory represents a subclass. So the subclass inherits from the superclass. I'm going to represent that just by having this little red dot here, and that's like a line representing that we remember that this subclass is inherited from that superclass. And then we of course have instances. So we might have an instance, and let's suppose that this instance is of the subclass. And I have this blue dot here to represent that Python remembers that that instance is an instance of this subclass. Now, whenever Python is looking for any method or instance variables, it's always first going to look in the instance. So it's first going to look inside of the instance, and it's going to ask, does the instance have that thing? If it doesn't, then it's going to look inside of that instance's class. and it's going to ask, does that instance of class have that instance variable or method? If it doesn't, then it's then going to look into the superclass. And in Python, that's just how superclasses work. By adding this extra layer of looking at the superclass for things that are missing in the subclass, what we do is we inherit everything that the superclass has and more. So this kind of gets to the question of when should we actually inherit from a superclass? Well, you should only inherit if your subclass should have absolutely everything that the superclass has, plus more, or maybe plus some small modification. So let's go over an example of this. So let's suppose that I want to represent books in a library. And let's suppose that we have two kinds of books. We have paper books and we have ebooks. So the way that I would represent that in classes is I would have one superclass for book. So I'd say class book. And every book is going to have a title and an author. So I'll say def underscore init, and that's going to take in a title and an author. And I'm just going to set self.title equals title, self.author equals author. And let's suppose that we have this underscore str method as well. And we're going to return title by author. Okay, so now I have this book class. I can create a new book, so I'll say my book equals a new book. And let's suppose that the title is The Odyssey. By Homer. And then if I print out my book, then I'll see that my book is The Odyssey by Homer. Let me actually add quotation marks around this when we print out the book title. Okay, now let's suppose that a library can have two kinds of books. Let's suppose that it can have ebooks and paper books. So both ebooks and paper books have everything that a book has plus more. In the case of a paper book, maybe we have a number of pages. So I'll say class paper book inherits from book. And I'm going to have a constructor that takes in a title, author, and num pages. And then I'm going to call the book constructor. So I'll say book._init with self, title, and author. Then I'm going to assign an instance variable num pages. So I'll say self.numPages equals num pages. So that's a paper book. Now let's suppose that an electronic book doesn't have pages, but it has a file size, like 3 megabytes, 5 megabytes, hopefully not a gigabyte for a book, but it has some size. So I'll say class ebook inherits from book. So just like a book, an ebook is going to have a title and an author. And I'll say def_init_ self, title, author. And then instead of num pages, it has size. Again, that's going to be the number of megabytes that this ebook takes up. So I'll say book.init with self, title, and author. And I'll say self.size equals size. Okay, so now let's say that my book is an ebook with The Odyssey by Homer, and let's say that it's 2 megabytes. So if I print out my book, then I can see that it's still The Odyssey by Homer. If I print out my book.size, then I can see that it's 2 megabytes. If this is instead a paper book, so let's suppose that I also have a paper copy of this book. My paper book equals new paper book, The Odyssey by Homer. And let's say that it has 500 pages. Then I can see that my paper book size. Oops, it doesn't have size. Instead, it has num pages because paper books don't have a size. They have num pages. So I can see that my paperbook.num pages is 500. So in this example, we wanted to create paperbook and ebook as separate subclasses because in this case, a paper book has everything that a book has. So in this case, a paper book has a title and an author. And so does ebook. So ebook has everything that a book has. So it has title and author. And paperbook also has this additional thing, num pages. And ebook has this additional thing, file size. So that's when you want to inherit, when you want to have a subclass that has everything that the superclass has, plus more. When you don't want to inherit is when you want to contain another class within a class. So let's go through an example. So let's suppose that I don't want these books to exist in isolation. Let's say that I want to have a library class, and libraries are going to contain books. So what I'm going to do is I'm going to say class library. And every library has some fixed number of books. So I'll represent that by saying def init self. And I'm going to say that every library starts off with 0 books. So I'll say self.books is an empty list. And then we can add books to our library catalog. So I'll say def add book, self, and then book. And here book is going to be an instance of book. So whether it's a book, a paper book, or an ebook, what we do is we add that book to our list of books. So I'll say self.books.append book. And I'll say def get size. This is going to return the number of books that we have. So I'll return the length of self.books. I'll actually give this a clear name, get number of books. Okay. So the important point that I want to highlight here is that even though there's some relationship between library and these book classes, in that a library contains a list of books, we didn't want to inherit from book, or we didn't want book to inherit from library, because it's not that a library has everything that a book has, it doesn't, or that a book has everything a library has, it doesn't either. It's just that libraries contain books. So rather than inheriting from books, I created a separate instance variable to actually contain this list of books that we have. So this is an example of what's called composition. So a library contains or is composed of a list of books, but rather than inheriting from the book class, then we want to have a list of books as our instance variable. So let's see our class in action. So let's suppose that I have the Ann Arbor District Library, AADL equals a new library. And I say AADL.add book, my book, and AADL.add book, my paper book. Now if I print out AADL.getNum books, then I'm going to see that my district library has 2 books. That's all for now. Until next time. Welcome back. Sometimes when creating an inherited class, you want to create a method that calls the superclasses method, but just does a little bit extra. Now, let me explain an example. So let's suppose that I have this pet class, and inside of this pet class, I have a method, feed. Now, suppose that I wanted to create something that inherited from the pet class. Let's suppose that I wanted to create a class dog. So I'm just going to draw out the beginnings of that class, dog. And I want it to inherit from pet, so I'll say pet in parentheses. Now, let's suppose that whenever I fed my dog, I wanted it to both call this feed method, but then let's suppose that every dog instance also has a little extra message. So let's suppose that a dog says arf, thanks, whenever fed is called on that dog. So if I did def feed with self, if I did this, And then let's say that I print out arf thanks. So if I define my dog class this way, whenever I create a new instance of dog and then call feed on that dog, then all that happens is arf thanks gets printed out. Because when I define this feed method, I'm overwriting the feed method in the parent class. So this would never get called. At least not by default, but there is a way to call it. So the way to call the feed method for this pet class, in addition to printing out this little extra bit of code that I wanted to run, the way that I would do that is I would say pet, capital P pet, so the name of the class, and then I would say dot feed, and I would call this on self. Now, notice that this is calling feed on the pet class. Normally when we call feed, we create a new instance, so I might say d1 equals a new dog. And normally I would say d1.feed. And I would pass in no arguments here because d1 is an instance. Here instead, I'm saying the name of the class directly, so I'm saying pet.feed. And since I haven't specified what instance to feed on, and since I haven't specified which pet instance I'm calling feed on, then I need to pass in the particular instance as the first argument to pet.feed. If I tried to say something like self.feed, here, then self.feed is just going to refer to the dog's feed method. So again, the way that I'll create a feed method on a subclass that has everything that the superclass's feed method has and more, I'll call the superclass's feed method by saying the name of the superclass, in this case pet, and then I'll say whatever method I want to call, and then I'll pass in the instance directly. So in code, this is what that might look like. So here I have a dog class, and the dog class inherits from pet, but it has its own feed method. Inside of that feed method, I first call pet.feed with whatever instance this feed method is being called on, and then I print out arf thanks after the pet.feed method has been called. Now, this also works for constructors. So let's suppose that I have another subclass of pet called bird. And let's suppose that the bird class has its own constructor, but I want to call the pet class's constructor as well. Well, the way that I would do that is I would say pet._init, and I would call it with whatever arguments I want to call. So in this case, I'll pass in self, and then I'll pass in the name. And what this is going to do is it's going to call the pet class's constructor on this new instance of bird. So it's going to set name, hunger, boredom, and sounds. So let's do some multiple choice questions. Okay, so this question asks, what would print when printout b1.sounds is run? So b1 here is an instance of bird. And if I'm calling b1.sounds, then you'll see that that's an instance variable that gets set right here. So here we're setting self.sounds equal to a copy of self.sounds. By default, every pet has a sounds list of merp. You'll see that the bird class has a class variable sounds set to chirp. So when I call pet._init, when it sets self.sounds equal to self.sounds, a copy of self.sounds, what that's going to do, because b1 is a bird, is it's going to create a copy of this list of sounds. And so b1.sounds ends up being chirp. So again, the reason that it's creating a copy of this list of sounds is because we have the superclass pet Then we have a subclass bird. So every bird is a pet. And then we have an instance of bird. And that instance is called B1. Bird has its own value for sounds. And pet has its own different value for sounds. Now, when we say b1.sounds, or self.sounds in the constructor, equals a copy of self.sounds, then Python is going to first look for what is the value of self.sounds. So let's go back to the constructor. So when we said self.sounds, here again, self is b1. So we're setting self b1.sounds equal to b1.sounds, and we're slicing it so that we create a copy of b1.sounds. When Python is searching for b1.sounds here, it first searches inside of the instance. This instance doesn't have a sounds instance variable yet, and then it searches inside of that instance's class, and so we find chirp, or a list that only contains chirp, as the list of sounds, and so here we end up creating a copy of that. So I mentioned all of that just to say that the answer to this is C. Or let's do another question. This question asks, for the dog class defined in the earlier window, what would happen when d1.feed is run if the pet.feed self line was deleted? So in other words, if we deleted or commented out this line, then what would happen when we called d1, which is a new instance of dog? What would happen if we called d1.feed? Well, so if this pet.feed self line was deleted, then the only thing in the dog feed method that actually runs is this print statement, print arf thanks. So remember that the pet feed method is never called by default because this method overrides that method entirely. So the only thing that would happen is print arf thanks would run. So that means that the answer here is C. That's all for now. Until next time.
Welcome back. We've created a special module that you can import called test. It's not available outside this Runestone textbook environment. In a full Python environment, you'd use a more sophisticated module, probably the one called unit test, but this one's a little easier to use and understand. We're just going to use one function in it called test equal, and it takes two values as input. If they're equal, the test passes, and if they're not equal, the test fails. So let's take a look here. We're importing the test module, and here we're invoking the test equal function from inside the test module. It takes two inputs. In this case, the first input is an invocation of the square function, and the second input is just a number, 100. And when we run it, it's going to tell us that the test passes. It passes because square of 10 is 100, and 100 equals 100. If I were to change one of these values, then the test would fail. It expected to get 101, but it actually got 100. So the way that we usually do this is that we make the first value we pass in something that we're checking on, and the second value is what it ought to equal. So it expected to get something that equaled 101, but square of 10 didn't actually equal 101. And of course, if I have this back at 100 and I do square of 9 instead, that's also going to fail because it got 81, but it expected 100. Now, one thing that's important to understand about this test.testEqual is that it's not creating errors. If it fails the test, the code execution will continue on. So let's see that. I can have something else on the next line, just another print statement. When the test fails, that doesn't mean that the execution will stop. So it said that the test failed, but it still went on to execute line 8 and print out the value 4. Here's an instructive example. We've got a function blanked. It's actually not correctly implemented yet, but we've looked at this before. It's something that's going to be used in the hangman game. It takes a word, that's the word to be guessed in the hangman game, and some letters that have been guessed already, and it's supposed to return a blanked version of the word. And we're supposed to write a test that if we pass in the word under, and D and U have been guessed already, what we get back should be U blank D blank blank. And in the code we have some examples of invoking test.testEqual. Our challenge is, what's the right invocation that will check whether the blanked function, when given under and D and U, will return this. So the correct answer is C, and let's see why. When we invoke the blanked function, we have to give it two values, the word, under, and the letters that have been already guessed. And then we're checking whether what came back from the whole invocation of blanked, whether that equals the U blank D blank blank. B and A aren't quite right. They don't have the syntax quite right. In B, we've sort of flipped. We've got the values in the wrong place. The blanked function takes a word and the letters that have been guessed so far. We gave it the blanked version of the word instead of the letters that had been guessed already. In A, the problem is that we actually passed 1, 2, 3 different values to the blanked function, and we didn't give a second value to the testEqual function. So we just have this parenthesis in the wrong place. So that's the mechanics of the testEqual function in the test module. You invoke it with two values, and it checks whether those two values are equal. It's a way to check whether a variable has the right value or whether a function is returning the right value. I'll see you next time. Welcome back. We've already seen how to implement a test for a function. You just invoke test.testEqual, where the first input is an invocation of the function, and the second input is the correct value, the correct output for the function. In this video, we're going to consider what tests are good to implement. And it's useful to distinguish between two kinds of things that a function might accomplish. One is that it might return a value, and the other thing is that it might have a side effect. And by a side effect, I mean that it might change the contents of a list, or change the contents of a dictionary, or it might also write to a file or produce some output in the output window. But we're not going to use test.testEqual for checking on writing to a file or the output window. But we will use test.testEqual to see if a list has been modified or a dictionary has been modified. So I'll call the two different kinds of tests a return value test or a side effect test, depending on what it is that the function was supposed to be doing. Let's first consider return value tests. So this is a function like square, where its whole job is just to compute a new value. It gets an input, it produces an output. It's not changing the contents of any list or dictionary. So which inputs should we give it as tests? And one way to think about that is to think about the equivalence classes of inputs. because we're not going to be able to test every single possible input. So maybe we should, for something that's computing squares or some arithmetic thing, maybe one equivalence class of inputs are positive numbers. And you already see we've got one test where we're passing in 3 as an input. But perhaps we ought to have another input which would be a negative number. Maybe if we somehow implemented this wrong, it would work for the positive numbers but not work for the negative numbers. So it would be a good idea to have a test of some negative value. That if we square minus 4, we should get positive 16 and not negative 16. It's also a good idea to think of, what other classes of inputs could we get? Maybe we could get a floating point number. Maybe it only works on integers for some reason. So suppose I had I need to do something where I can actually compute it myself. Let's see, 1.5, what's the square of 1.5? It should be 2.25, I believe. Let's check that to be sure. Yes, I've passed all 3 of those tests. You'll notice this is an important point, and when you're writing a test, you got to figure out which inputs should you run a test on. And you have to know what is the correct output. In that case, I was a little unsure about the square of 1.5, but it is 2.25. And then you also should think about sort of the boundaries between these equivalence classes. So I did a positive number, I did a negative number. Gee, what happens if we do 0? Will it get that right? So it's a good idea to have a test for these boundary conditions, these edge or extreme cases. It's also helpful to think about what might go wrong. Like, what could I possibly do wrong? And this is a very simple function. It's hard to think of things that could go wrong, but maybe I did it with a plus instead of a times. If I were to do test.test equal square of 2, I would still get this right. So I've failed most of my tests, but square of 2 came out to be 4 even though I did it wrong. And so 2 isn't really a great choice, or if I do 2, I should also do something like 3 that would distinguish between a correct implementation and an incorrect implementation. It's also worth thinking about return value tests for functions that have optional parameters. If a function takes an optional parameter, one of the edge cases to test for is when no parameter value is supplied during execution. So let's consider the built-in sorted function. You remember that it has an optional parameter reverse. So I can call sorted of 1, 7, and 4 and not specify any value for the reverse parameter. It's optional. And if I don't specify the reverse parameter at all, I should get the results not reversed. I should get 1, 4, and 7. If I call sorted of 1, 7, 4 with reverse equals true, then I should get the values in the opposite order, 7, 4, and 1. So I should pass both of these tests. Now just to be complete, I might want to have one more test here, which is what happens if I call sorted on 1, 7, and 4, but I say reverse equals false. So I've actually provided this parameter. I should get the same value that I would get if I left out that parameter entirely and just got the default value, because the default value is false. So this one should pass as well. But of course, if I changed any of these, 7, 1, and 4, now I'm going to fail the second test. It said we expected to get 7, 1, 4. This is what we specified was supposed to be the value, but we actually got 7, 4, 1. Now in this case, we failed the test because I wrote a bad test. The correct answer, when we pass 1, 7, 4 to sorted with reverse equals true, the correct answer is 7, 4, 1. And now we've passed it. In summary, You'll use a return value test when the purpose of a function is to compute an output from its inputs. You express the test by calling test.testEqual. The first parameter is an invocation of the function. The second is the correct output, which you had to compute manually. You should make one test case for each of the equivalence classes of inputs, and don't forget the edge or extreme cases. When you're dealing with a function that has optional parameters, some of those edge or extreme cases should include omitting or including the optional parameters. Now, the art of creating test cases is that you're going to create several of them. When you've correctly implemented the function that you're testing, you will pass all of the tests. But you want to have what's called good coverage of those tests. They need to cover all the ways in which you might make a mistake in implementing the function. So if there was some error in the implementation of the function, then one of your tests ought to fail. But if the function is correctly implemented, it should pass all of the tests. The art of this is to pick a good set of tests so that you'll fail if the function is not implemented correctly, but you'll pass them all when the function is implemented correctly. I'll see you next time. Welcome back. Here's a function that is supposed to have a side effect on one of its inputs. The function is called updateCounts, and it takes a string of letters, and it takes a dictionary as input. It's going to do some stuff. It isn't returning any value, so it's going to return none, but it's going to have a side effect. CountsD is going to be changed. It's going to be mutated somewhere in here. On line 3, it's doing something. On line 5, it's assigning to CountsD. And so if we want to check whether updateCounts is working correctly, we need a side effect test. To do a side effect test, you're going to set up some known initial value for an object. You're going to run the function, and then you're going to see if that object is updated correctly. So in our case, we're going to create a dictionary on line 9. It's got two keys, A and B. We're going to call updateCounts on line 10, and then we're going to check on lines 12 and 14 two different tests to make sure that the counts dictionary has been updated correctly. Now, what is updateCounts supposed to do? Well, it's supposed to count all of the letters that appear in whatever string is passed into it, like AAAB. In this case, we're passing in a string that has 3 A's and 1 B, and we're supposed to add. If there are 3 more A's, then this A should become 6, and there's 1 more B, so the B should become 3. And that's what you see as the tests. We check at the end, is counts square bracket A equal to 6, and is counts square bracket B equal to 3. Let's check whether the test is actually working. Turns out it's not working. There are errors in there. And we'll come back and we will fix that function as we go along here. But before we do that, let's think about other tests that we might want to have besides just the single test that we have here, where we have the original counts dictionary on line 9, and then we call updateCounts on line 10. What other initial dictionary might we want to try to pass into updateCounts, and what other strings might we want to pass in? So I have a couple of ways for you to think about how to decide which tests to run for a side effect test like this. The first is just to think about edge cases. What if we were to start with an initial counts dictionary that was empty? And I'm first going to get rid of all of our markings here. So another possibility might be that we start with an empty dictionary and we call updateCounts and then we check something about what it should equal at the end. So counts square bracket A should now be 3. There weren't any A's in the dictionary. We didn't have a count for A's. We have 3 A's that we've passed in, so we should now have a total of 3. So that's one possibility. Another edge case would be passing in an empty string. So maybe we have the same counts dictionary that we had up here. And now we're going to pass in to the update counts function an empty string. And then we would want to do tests to make sure that the counts haven't changed. So count square bracket b was 2. It should still be 2 because there weren't any characters in the string that we passed in. Some other possibilities you can imagine, maybe we call update counts and we pass in a dictionary that has the same name as it does inside. And then we would have some tests to make sure that counts D has been updated appropriately. We could pass in a character string that includes letters that are not in the dictionary, as we did already up here. So that's one way to think about it, is just sort of ask yourself, what are weird edge cases? And another way to think about it is to kind of look at what will be in your code for update counts and think about exercising all the paths through that code. So we're going to have a conditional. If C is in the counts dictionary, that's checking, is this character C new? So we ought to have two tests, one for the possibility that a letter is in the dictionary already and another where the letter is not in the dictionary. Or we could include both in the same test, a string that has the letter G in it, as well as A's and B's. The other thing is, in our update counts, there's going to be some iteration where we're going to go through all of the letters. And so we're going to have some kind of for loop. And an edge case for iteration is when you iterate through something that's empty. So that's why it's a good idea to have some update counts where we pass in an empty string. That's going to exercise a path through this for loop where we just skip everything inside the for loop. All right, so now we have a bunch of tests. Let's say after I call this update counts, I should have another check on test.test equal counts D square bracket A ought to equal 3. So if I run this, we're going to find most of our tests have failed. One of them passed. That if we pass in a counts dictionary that's initially A has 3 and B has 2, and we update counts with an empty string, we're still good. Counts of B is still 2. It didn't get mistakenly updated. But we've failed most of our other tests. So let's see what we would have to do to correct the code here. So let's take a look at our first test. We're passing in this dictionary A3 and B2. That's going to be the second parameter. The first parameter is the string AAAB. And we're expecting that A should be 6, but it's actually 2. So it starts with a value of 3 and it ends with a 2. And you can look in the code and you can see what's going wrong here, is that when we first encounter the letter A, so now the variable C is bound to the letter A, we are setting the key A in the dictionary to have the value 1. So it used to have 3, but now it's getting set to 1. C is in the counts dictionary, and then it's getting incremented to 2. Each time we encounter an A, we keep resetting its count to be 1. So my problem is that I'm always setting counts D square bracket C to equal 1. But I really should only do that in those cases where it's not already in the dictionary. So this ought to be inside an else clause. Should be conditionally executed. And now I think we're going to pass some more of the tests. In fact, that's sufficient to make it pass all of the tests. So that's side effect tests for you. You create a side effect test whenever the function is supposed to make changes to a mutable object. You set up an initial value for a variable, like I did on line 11. Then you run the function, like I did on line 12. And then you see if the object that the variable is bound to has been updated correctly. That's what happens on lines 14 and 16. I'll see you next time. Welcome back. Testing a class definition involves creating instances and invoking methods on those instances. Here's a little class that lets us define points on an xy plane. Instead of just treating them as two numbers or making a tuple, we're going to actually make an instance of a class. Each instance will represent one point, with an attribute for its x position and another for its y position. I'm going to draw a little grid again, just so we have a place to plot our points. And so we can have a point like 3, 4, which would be plotted there. So to test our definition of this class, we're really going to have to test the three methods that we have. We have a constructor, the _init. We've got the distance from origin, and we've got the move method. Let's start by doing the constructor, because that's really the heart of any class. How do we test if we've implemented this _init, the constructor method? How do we test if we've implemented it correctly? To figure that out, you've got to remember the mechanics of classes. So basically, we create a new point by invoking the class. When you call point on line 19, you will create a new instance of the point class, and then behind the scenes, the constructor, the init method, will be called, with 3 getting passed as init x, 4 as init y, and the new instance itself will be bound to the self parameter. Now, the purpose of the init method is to change the contents of self. Initially, self has no attributes, but after we've finished executing the init, then self should have 2 attributes. It should have an x attribute and a y attribute, and they should be bound to the corresponding values 3 and 4 that have been passed in. So to test the class constructor, we create a point, and then we check whether it has its attributes correctly set. Is its y attribute set to 4? Is its x attribute set to 3? Now usually when we're doing a side effect test, we would have to create an object like a list or a dictionary, and then invoke a function, and then see if the list or the dictionary has appropriately changed. In this case, we didn't have to do that because the invocation of the point class both creates the instance and invokes the method. So those two are combined into one step. But then afterwards, we run our tests to see whether it came out right. By the way, if this is a little confusing for you because you're just coming from learning classes and the mechanics are a little hazy, running this in CodeLens on your own would be really helpful to make sure you understand what's going on. Now the next method that I'm going to show you tests for is the distance from origin method. And you can see that that distance from origin method, what it's supposed to do is tell you how far away the point is from the origin. In this case, it's a distance of 5. If we picked some other point like 2, 2, it would have a different distance. But the 3, 4 point should have a distance away of 2. And so in order to do a test,
this is a method that just returns a value. It doesn't change the contents of the point, and so we should be doing a return value test. And I'm just going to get rid of a few of these markings. So testing the distance from origin method, this is a return value test. I still need to create a point in the first place. I could have actually just used the p that I defined on line 19, but when I'm defining a test, I like to have everything that's involved in the test right there. So I'm recreating a new point p that's at position 3, 4, and then I'm checking, is it a distance 5 away from the origin? And I should have some other tests as well. I should make some different points that are different distances. I could check whether a point at 2, 0 is a distance 2 away from the origin. And finally, I've got this move method. Now this move method, what it's doing is taking a point, like this 3, 4 point, and it's going to translate it. It's going to make it move some distance. So we'll pass into the move method a distance to move in the x direction and a distance to move in the y direction. So in order to test that, that is a method whose purpose is to have a side effect. It's supposed to change the point, and therefore I need to have a side effect test. So I'm going to create tests here that, again, I create my initial point, and then I move it. So I'm moving it -2 in the x-plane and by up 3 in the y. So I'm going to go -2 from 3 over to 1, and +3 in the y. So I should end up at 1, 7. So in my test, I'm checking. So first I create the point, then I move it, and then I see if it has correctly been moved. If my move method is correctly implemented, the x value should be 1, and the y value should be 7. So in this case, we'll run our tests, and we'll find out whether it's all correctly implemented. It is correctly implemented. If I had made some change, or if some of these methods weren't defined yet, then I would fail some of the tests. The purpose, again, of having these tests is to check whether the implementation of the methods is correct. If the methods have been implemented correctly, you should pass all the tests. If they haven't been implemented correctly, then one or more of the tests will fail. So that's a skeleton of how to test a class definition. Basically, you need to assess for each method whether its purpose is to return a value or have a side effect. Testing the class constructor is special, because each test will invoke the class with some parameters and then check whether the returned instance has its instance variables set correctly. For the other methods, you will also have to create an instance, but then you invoke them and either check whether the return value is correct or check whether the instance has had its variables changed appropriately. I'll see you next time. Welcome back. Writing automated test cases is a bit of an advanced topic for an intro programming course like this one. We've included it because it's a preview of an essential software engineering practice for larger projects, and it's a good idea to start developing the habit of testing right from the beginning of your programming career. Moreover, the idea of edge cases is an important way to think about what your program needs to do. Indeed, more generally, you may find that the notion of edge cases influences how you think about processes beyond the realm of computer programming. For example, when I think about grading policies for my on-campus courses, I like to think about edge cases. What if a student gets sick the night before the assignment is due and then hands it in late? What if a student skips some of the required assignments but then demonstrates mastery of the material by getting 100% on the exam? Those are edge cases that I need to have policies about. I need to decide what is the correct grade to assign to students when those unusual circumstances occur. Learning to express your test cases as invocations of test.testEqual is also a good way to reinforce your understanding of the mechanics of functions and of classes. At this point, you should be able to use the test.testEqual function to express test cases, identify when a return value test is needed versus when a side effect test is needed, and you should be able to identify and express edge cases for functions and for class definitions. Testing. Testing. 1, 2, 3. Testing. Is the mic working? Are we on camera? Oh, hi everyone. That was just a little joke about testing. That's all on testing for now. Bye everyone. See you next time.
Welcome back. Now remember that there are three main kinds of errors that we can get when writing Python code. There are syntactic errors. That's when Python doesn't understand how to read the instructions in your program. So for example, if I forget a bracket or a parentheses and I try to run my program, then I get a syntax error saying that Python didn't understand the instructions that I gave it. Beyond syntactic errors, there are also runtime errors. Runtime errors occur when Python understood the instructions that I gave it, but something went wrong when Python tried to run those instructions. So for example, if I run my code right now, I get a runtime error, or more specifically an index error, because even though Python understands that I'm creating a list and assigning that list to items, and then I'm assigning third to be the third item in items, because item only has two items, A and B, when I try to fetch index 2, then I get an index error, which is a kind of runtime error. So in other words, Python understood what I wanted to do, but something went wrong as Python was trying to execute my code. And then finally, there are semantic errors. And a semantic error is when Python successfully ran the code, it just wasn't exactly what I wanted it to do. So for example, if I wrote a function to add two numbers, and that function actually divided two numbers, Python isn't going to give me an error, but I'm also not going to be happy when my code divides the numbers that I wanted to add. So when we have a syntactic error, Python doesn't run our code at all. When we have a runtime error, Python runs our code until it encounters the runtime error. And when we have a semantic error, Python runs our code, but it just doesn't end up being what we wanted it to be. Now, usually when we encounter a runtime error, then Python is going to stop running our code as soon as we encounter the runtime error. So for example, this code again gives us an index error. So let's suppose that I modified my code and I had something like print, this is not going to be reached. Now if I save and run my code, you'll notice that this line 3 doesn't print out because this expression results in a runtime error. So again, when you get a runtime error right here, then our program just stops running and throws, in this case, an index error. If I had a print statement before this line, this is going to be printed, then this would successfully execute. So in this lesson, we're going to learn about try except. What try except does is it allows us to handle runtime errors and to tell Python what to do when it encounters a runtime error so that it doesn't suddenly stop running your program every time it encounters one. So let's say that I wanted to run the code after assigning third. So let's suppose that again I have a print, I want this to run statement, and I want this line to print out even if I encounter a runtime error on line 2. The way that I can do that is by putting that into a try except block. So the simplest way to write a try except block is just by saying try, and then colon, and then code inside of the try block, and then I can write except, colon, and then code that I want to run if some runtime error happens. So let's suppose that if I get a runtime error while running line 4, let's suppose that I want to assign third to be false. So I'll say except third equals false. Now when I run my code, it's not going to show us a runtime error anymore, but instead I actually am able to reach this print statement even though I get a runtime error right here. So to see what's happening, I'm going to add a few more print statements. So inside of this except, I'm going to print something went wrong. And I'm going to add print A on line 4. And after assigning third, I'm going to print out B. Okay. When I run my code, you'll notice that I have print A executes. Then when I set third equal to items 2, this gives us a runtime error. And as a result of this runtime error, print B you'll see never executes. So what happens is, as soon as I get a runtime error for any line in this try block, then Python jumps right to the except block and starts running what's in the except block. So you'll see that something went wrong, gets executed, and then here we assign third to be false, and then I want this to run, gets executed after that. Now let's suppose that we didn't actually have a runtime error. So I'm going to clear my output, and I'm going to make it so that items actually does have 3 items. Now if I run my code, then what happens is I never get a runtime error when assigning third because I actually have a third item here. So A gets printed, third gets assigned to C, and then B gets printed, and then we completely skipped the except block because nothing went wrong, and then we print out, I want this to run. So in brief, what try except does is it says, try to run the code inside of this try block, and if something goes wrong while you're running that code, rather than stopping execution of the whole program, just jump and run whatever is inside of the except block. If nothing goes wrong, then we just skip the except block entirely and run what's after the try except. That's all for now. Until next time.
Hello and welcome to this addition to The Way the Programmer. So my name's Charles Severance. I teach Python courses. I teach web development courses. And so I was tasked with giving you a real-world example of object orientation. And it's a little difficult for me because in the real world, little tiny programs tend to not cause us as programmers to build or even use objects in a sophisticated way. And so I've decided in this that I'm going to try to take you into a lot more complex world and give you a sense of what's going on behind the scenes and how object orientation is essential. And so I'm going to actually use Django, which Django is a web development framework. And this is less about writing Django than it is about looking at how Django uses objects to interact with you as a programmer who's going to write Django. So if you really want to, go crazy on this, go to my website, dj4e.com, which is under construction. I'm not really teaching this course until a couple of months from now, but this will be eventually, by the time you're watching this, maybe this will be far more sophisticated. The thing I'm working through is what's called the Django tutorial, and this comes from the Django community, and this is where a lot of initial Django developers, they just say, hey, you want to get started? Go ahead and get started. And so we're going to go through like the first 1 and 2, but I've already done that. And this is not about Django. This is about object orientation. So I'm going to play with these things and show you some of the source code. So it might be good if I showed you the eventual source code that I'm trying to weave a narrative that we get to. So let's take a look at that source code. So if I go into polls 2, this is a little application. It doesn't do much. Right now it just prints out hello. Oh, I got to start the server. Hang on. Manage. Oops. cd ... Oops. So I have the server running. This is a little application. Oh, I got to go up a directory. Now it's running. Okay, so this is a little application that is only at the second step of the tutorial, and the only thing that it does is print something out. And as such, it's not a very sophisticated application. And I'm going to talk to you about 3 files. The first file is a file called the URLs file. And the URLs file is very simple in that it basically says, for this particular path, which is the path that has nothing here after that slash, run this code from the file views with a method named index. So if I look at views, this is the view code, and it basically is saying return an HTTP response, because this is part of the request response cycle, hello world, and that prints this thing out. And it's calling a bunch of things. Believe me, and I'll show you a little bit of how tough this would be if we didn't have Django doing all this work. And so this is the code that we have to write. And then there's the other thing that we're not going to cover too much about is how to create database tables. And here's this models file, and this class basically says, let's make a question model, which is also then a table in the database, and that is extending an object that comes from Django called models.model. And if you look down, this is the code that I've got to do, and it creates fields in the database and all these other things. If I took a look at what this database is, it ends up with all this other stuff and has all these files that are created for me. There's data in these files, and I mean there's structure in these files, et cetera, et cetera. And all I did was created this. And so there's a sort of a very small amount of work that I had to do to sort of get Django to do a whole bunch of work for me. And I do that by extending an object that I'm handed. This models.model object is something that I'm extending. So at the end of the day, what I want to do is I want to look at what it takes to take a URL and have a piece of code that responds to that URL. So here's some URLs. I want to show you how Django works and what Django gives you in a way that makes building Django code way more easier than it could be. So if I was to build a web server, and I've written here, and I'll show you this code in a second, I've written sort of the simplest raw Python web server that I could write. And basically, at some point, a browser is going to type a URL. It's going to send a request over the internet to your computer. And in that computer, there is like an operating system, whether it's a Mac or Windows or Linux, and it has networking capability, TCP/IP. And there are documents that if you really wanted to, you can learn how to build those things. You can type into Google RFC 791 or RFC 793, and then you can go get a sense of like how hard that really would be. And I don't know if you played with sockets or not, but there is a socket library inside of Python. And then we're going to create a very simple web server that's going to sort of receive this request from the browser and then send back a really tiny little HTML bit that's going to be sent back to that browser. Very tiny HTML. Little body tag, hello world, /body/HTML. And all of this stuff, I'll cover all this stuff, how we create this server. And this just gives you, I mean, this isn't even a real web server. It's not reading files or anything else. It responds to every request with hello world over and over and over again. Okay, and then the next thing we're going to show after that is we're going to show how those 3 files that I showed you, models.py, urls.py, and views.py, we write 25 lines of code, and then we've created this application that's very sophisticated and it's very capable. And then after that, I'm going to show you sort of the detail of how within Django creates objects that then you extend to communicate with Django how you want your application to work. So we're going to start with a very, very low level concept of how a Python program would talk directly to a web browser. Okay? And so let's go take a look at, first let's take a look at this server code. Let me start a new browser. Let me actually get rid of, well, the Django server can stay there. cd dot dot, cd dot dot. And you can download this from dj4e.com. Let me make this a little smaller so we can see it all. Okay, so if you were, here's some Stack Overflows that I used and some Python documentation that I used to figure all this stuff out. This is not particularly an object. This is a socket library that's built into Python already. And then if we take a look, one more line. Oh, I have to put a try except around all that stuff. So we're going to print, here's how you get at this thing. We're going to call this the create server function. And server socket, we're telling it to start a socket. A socket's a little different than a file. It's kind of like a file handle, except that it's a two-way thing, which you can both read and write to the same thing. It's you could write to a file because it's like two sides. If you have one application and they're both connected via socket, one side can write and then the other side can read, and then the other side can write and it comes back. And so it's almost like two connections. A socket is a bidirectional or a two-way connection. So we're starting a socket. This is the server side, because in Django you're building the server side, not a browser. A browser is the client side. This is the server side. And we wrap this whole thing in a try and except because I need to close these sockets. If you're writing this code, it took me about an hour to write this code, even after I found it on Stack Overflow. So you don't really want to write this. And I'm glad it worked. You can look at it, you can play with it, but its whole goal of this code is to prove to you that you don't want to write this code. And so I'll just walk through it. What we're doing is we're going to be a server, which means we are waiting for connections, and that's what serversocket.bind says. Wait for a connection on port 9000. Serversocket.listen 5, that means up to 5 connections. And then this while loop basically says accept the socket if the socket has arrived. So it'll actually stop here until a socket connection happens. So when a browser makes a connection to your server, it sits here. Well, it sits here until the browser makes a connection, and then it drives down, and it gets these two pieces of data, which are a tuple, but this is just an assignment statement, right? Client socket address, the address of what the browser's coming from, and the socket object. So this is now an object. So client socket is an object that's populated by the statement. So if you were to read the HTTP protocol, you would realize that the first thing the browser is going to do is send us a command like get or post with the URL that it's interested in. And so we're going to read the first 5,000 characters from the browser, and then we're going to decode it. I'll split it based on new lines because it's actually a series of lines, both the HTTP command and then a series of header values. And we're going to print the very first line, which you're going to see how this works in a second. And then we know what the HTTP protocol is, so we're going to just send back this simplest of HTTP pages, which is a 200 OK, which says this is a valid document, here you are. We're going to send back UTF-8 HTML and then a blank line. So here's the blank line right here. And then we're going to send the body with 2 new lines at the end. And of course, because we're sending it outside of our world, we're going to do a data.encode so that the UTF-8 is properly sent. So we're going to receive UTF-8. That's where this decode came in. The GET request that comes into us is going to be UTF-8. And then we're going to send back a document that's also UTF-8. That's also why I told it it's UTF-8. And then encode is what converts the Unicode inside of Python into UTF-8. And then we have to kind of shut it down, which the shutdown sort of sends all the data, makes sure the data gets received, and then takes the socket. And then we go back up to the top, and we wait for the next socket. So that's each one of the URLs that gets retrieved is going to be handled. And so if keyboard is if I hit Control-C or Control-Z, and it shuts down but closes the socket, it turns out it takes like a minute or two to be able to start it back up again unless you do it. Or if like you type in change in this, you make a mistake, you'll probably generate yourself an exception, and we still want to close the socket if we made a mistake inside here. That was really helpful for me because it took me a long time to get this code to work, and it blew up a lot. And so now it's not blowing up. So now let's run this. Okay, and I can say Python 3 server.py. And now we have the world's simplest Python server. And so if I go into my browser and I go to localhost 9000, that's the port. It's like an extension on a phone system. So localhost 9000 says connect localhost, which is the same computer that I'm on. This is not really leaving to the internet. That would be a normal domain name. 9000 says on 9000. And my Django was running on 8000. And my little mini Python server is running on 9000. So I'm going to copy that. I'm going to go into Google Chrome. I'm going to turn on Developer Console. And then I am going to watch the network. And then I'm going to type in that URL. That's just junk, so we don't want that. I don't know what that's doing. So I'm going to hit enter if all goes well. Yeah. So it says hello world. See that? Pretty awesome. After all that work. So what happens is if you go down here, you can see that, where is this? I don't want to see. Yeah, I don't want to see that. So we sent a request to the local host on port 9000. We did a get, 200 OK. Remember our application said 200 OK, wherever that was. See this little 200 right there? 200 OK was the status that our browser got back from our application. The response headers. The response headers said that, oh, this is a HTML document with a character set of UTF-8. Oh, looky, looky, looky. We did that. We said that in our Python server.py code. And the request headers, this is all that stuff. This is the browser telling us what kind of browser it is, et cetera, et cetera. And where that shows up is, remember I did this split. By only showing pieces sub-0, I'm not showing you any of those things. But if you just were to print out this RD variable in your version of it, you would actually see all of those headers. And that's the HTTP request response cycle. That's like the simplest version of the HTTP request response cycle. Now, if we take a look at this, we'll see that this is also retrieving the document favicon because it's trying to return the icon that would show up right here. And our web server is not smart enough to give back icons. It only says hello world to every single request because it went around twice. It did this for localhost / and then favicon. It did it again, and it simply sent back a document. Now, after a while, we could say, oh, this char type is image JPEG, and then we would have different body, and then we could send favicons back and forth. And if you'll notice, it prints out at this print statement right here. This print statement right here prints out the GET request, which is, this is the first request that corresponds to that local host. This is the second request that corresponds to that favicon. Okay. And so we got 2 requests. And now I'm going to blow this up, and that's when it's going to hit the keyboard interrupt, and then it's going to shut down, and then it's going to finish that. So that server.py was how a web application works, but this is like such a tiny fraction. If you really wanted to build a real live web application that had multiple files and CSS and images and all that stuff, it gets harder and harder. And then receiving data, there's parsing of the incoming data. And if you Google like the RFC for HTTP, or RFC stands for Request for Comments, you will find RFC 2616, the Hypertext Transfer Protocol, that gives you some subset of how much information you need to know to write a web server and to write a web browser. And so I'll just start to skim down. We got hundreds of pages. That was just the table of contents, goes down to 176. And this is one of many documents that describes how that works. So it turns out that code that I wrote is not entirely compliant. It's just barely good enough to do the most crude and simple version of this so that you can look at it and you could play with that. You could add print statements, etc., etc., etc. So if you were going to want to write an entire browser, you have to figure all these things out, right, in Django, like the 2616 Hypertext Transfer Protocol. You'd have to write all this. There's all these other rules. And so I think what I'll do is I'll stop now, and then coming back, I'm going to show you how Django implements that exact same thing, but then how your code hooks into Django in a way where you're using object-oriented programming to hook the code into Django in the right places so that the amount of code that you have to write is really small and the amount of documentation that you have to read is extremely small. And then someone inside Django had to read lots and lots of things about how to make this stuff work. So when we come back, we'll talk a lot more about your relationship between the Django code and your code and how that relationship is done through object-oriented programming. So welcome back. Now what I want to do is I want to dig into a little bit about how you, as a developer of a Django application, interact with Django itself with objects. So just recall, if you're looking for the downloads, djfree.com is the place to go. We are working through the Django tutorial, and I'm pretty much no further than part 2 in this particular one because I'm really not worried about building the Django app. I'm really interested in how objects work. So one of the things that you can do, because Django is really cool open source, is we're actually going to look at the source code to Django. Django is open source and has 26,000 different separate modifications, almost 1,700 contributors, and it's a lot of source code. It's probably 1 million lines of code. And so this is real enterprise software. It's very exciting stuff, and open source is really cool because we can look inside Django. Django is not a magical thing that we can't see, and we can learn from it and understand it. And so what I'm going to try to do is I'm going to take you inside Django, and our application that we write is going to be really simple. It's this polls application that just prints out hello world, because this isn't a Django class. This is really kind of how object-oriented works inside Django. So what we're doing here is, if you read the Django documentation and you read the Django tutorial, what you find is that, oh, okay, there's this big thing called Django, and you got to write these files, this file URLs that routes things, and models that creates database tables and allows you to read and write data from those database tables, and the views that shows what the user interface of this is. And so you're supposed to create these files. So I'm going to focus mostly on the models file and talk a little bit about what's going on inside of Django and how Django in effect creates classes, and then you create classes that derive from the Django classes, and then you can create objects that are based on your classes and then use those objects. And so we're going to dig into the source code to Django. And so this particular one, let's take a look at this base.py. Let me show you the models file that's our code. So here's our models file. And if you read the documentation in Django, it says, well, if you want to create a database table, it's called a model in the model view controller. We're going to make a database table that has question text, publication date, and then have some methods inside of it, like how to print this particular object out as a string, and then this was published recently as something that they're going to use in it. And then we're going to have another table called choice, and it's going to have a question column and a text column. And we can see this. There's this thing called migrations that reads this and creates tables. And so in here, we have polls to choice question, polls to choice, which has those columns, and it's created this database table for us. All we did is we took this thing not only allows us during runtime to read and write from the database, but it also at setup time, it creates things for us. And so these two database tables that I've got sitting in my database here were created from this object because it runs one process to read through your objects, then create database tables. It's another process while it's doing request response cycles, then it actually reads and writes the data in the database. So that's one nice thing. And so models.model is a class. And if you just look at this, we're creating a new class that's question. It's our class. And we're extending the models.model class. And we're doing this to inherit lots and lots and lots of functionality. And then the definition of this is just, variables, models.char field. That's a variable, a constant with some stuff, and these are objects, and all this stuff is kind of sitting there for us to sort of, it almost creates it's almost like a dialect of Python that is specifically to define these database models, okay? So if you know that this is a class and that it's extending another class, let's go find the source code to that class. So now what we're going to do is we're going to go into the Python GitHub repository, and here on line 383 in the base.py, this big long thing, if you're looking for it, it's linked here from this slide right here. And now this is Django code. This is the code that was written by the Django project. And so they made this model. And if you look at this, you've made simple classes. This is not that different than the classes you made, right? So you have an underscore init method, and the first parameter is self. Now that should look familiar to you. And then you have a couple of arguments, and then we got a whole bunch of code. And so if we start looking down here, this is just the constructor. So part of the goal of object-oriented programming is you get to write a little bit of code that leverages hundreds and hundreds of lines of code that somebody else, some other really sharp people, like let's see if we can find the contributors. So this is a list of all the people that built this. These people know a lot, right? There's a whole bunch of people, and we can see their work and what they're doing and how long they've been working. And they're doing things like reading all these documents, like the Hypertext Transport Protocol and this and that, and knowing how to talk to databases and knowing how to talk to SQLite database and how to talk to MySQL database and a Postgres database and Oracle database. You literally don't need to know anything. And so what they're doing is they're building a really large object or class that then you can extend, and you don't have to write all this code. This is very general purpose code. Part of the goal of writing an object is to hide this from you. Now, we can look at it. You shouldn't have to look at it. You should be able to look at the documentation, i.e. the documentation on these little tutorials. I'm just trying to give you the sense that here we go. And so this is still the constructor. This is the initialization, the constructor, right? So now we have a method, okay? And so these are other methods like and these are things that you'll sort of recognize. The double underscore, string underscore, that's what happens when we convert a model object to a string, underscore underscore. So this is no different than if you convert a dictionary to a string. There's a little method inside of Python that's double underscore, string, double underscore. EQ, that's comparing equality. Hashing has to do with how dictionaries work. Get state, set state, and all these things are just the kind of things that if I am the Django developer, I have to do this because that lets me mount my class into Django the right way. And these are methods that would be documented, like serializable value, save, and there's another like whole bunch of stuff. See how much work at save base. You should probably be looking at the Django documentation to see all this stuff. Save parents. We're still in the model object, right? Get an extra preview. Okay. Prepare database save, clean, validate unique. And so this is just code that was written by these people. Where are they? Right? All these people wrote all this code and read all the documentation and tested the heck out of it. And you just write this code right here. And you extend and you inherit all that stuff. And that does things like creates all the tables, which I showed you. It actually hooks into an administrator interface. Let me see if I can show you that. So this is an administration interface. And so this user interface, this part of your Django application that came from Django, that's the admin tool, the admin panel within Django, and your model is now in there, right? And so you got some question text and a date published, et cetera, et cetera, et cetera. So all you did was created one little file, right? Django's this magical thing, administrator interface, database creation, table creation, et cetera, et cetera. You created this little file, and away you go, okay? So then I'll show you one more thing. The pattern you'll see is kind of the same, is in this views.py file. So this is returning a response when you go here into the Polls2 application, right? It returns this response. But if you were to look at this at the developer console, under network, you would see that there is a whole bunch of stuff that you've got to do HTTP. We sort of saw that in the first video, like the response headers, all these things, what the content like is, what the type is, the date, these things, and there's many other these things that might be necessary. So you could learn how to write all these things, or you could basically say, you know what, I'm just going to inherit the obvious things, and I'm going to return, you read the documentation, on HTTP response. So this is an object. This is the constructor to that object, and we're going to send in a string to the constructor. So this HTTP response, we could create it, we could set headers, we could do all kinds of things in it. Not just the text, but all kinds of other things that have to do with the HTTP protocol. And so somewhere inside of Django, they have defined this object that's the HTTP response. And so I can show us that one as well. Take a look at the HTTP response. And we're using it in a very simple way. But if you look inside Django, you see there's a lot to it. So here we go, is content is a set of bytes in this case. And that's the constructor, right? Then there's serialization, etc. And so all these things, all those things are part of that object. And HTTP response base, if we go find that one, which I think is just up here. So even within this file, they're using one class, HTTP response base, right? Content type, that's the thing about it, text/HTML, status, that was the 200 OK, et cetera, char set, UTF-8. So we're setting that thing up. That's a constructor here. And if you were looking at the documentation, you would see that. The char setting the char set. Setting a cookie. A cookie has to do with this little bit of data that goes back and forth between the server and the browser. You don't have to know how to do that. You could go read that. You could go into RFC 2616. RFC 2616. See if I got that. Look at 2616. And then we could search for cookie. Whoops, how come I don't see that? Oh. RFC 26, RFC HTTP cookie. Which one is it? Maybe it's got its own document. Yeah, there we go. RFC 6265. So if you want to set a cookie, which is how we log in and out of applications, you got to go read this one. And how many pages is this? It's only 37 pages. But it turns out that, thankfully, somebody in the Django project, where are we, has a little, has a method called setCookie for us. And so if you were to go look at the documentation, if this HTTP response wanted to set a cookie back in the browser, instead of reading all this stuff, some kind person who helped write Django wrote all this down and gave you a method called setCookie. So I'll stop there. I'm not really trying to get you to sort of be a wizard in any of this stuff. I'm trying to give you little tiny places where you can jump in and learn more. The basic idea is there's lots of complexity to this, lots of documentation, lots of rules about how to comply to this stuff. And Django has made it so that that's all hidden behind this abstraction boundary. You have objects, you make those objects. So we played with the models object, and then we played with the HTTP response object. And we can use as much or as little. We didn't have to use the cookie in the response object. We can use as much or as little of that stuff as we want. And that's the beauty, is that all that complicated detail is hidden inside Django with the convenience of we can use as little or as much of it as we want. So I hope you didn't try to write Django because of this. I just wanted to make a little connection with how you work with large frameworks or large libraries, and how object-oriented programmings and the patterns of abstraction and hiding and inheritance can be put to good use, both by building libraries and then by using those libraries. I hope you found it useful. Cheers.